Good evening, ladies and gentlemen. I'm Rick Maxwell, and I'm a mentor for the Dirty Mechanics Team 3932 in Boca Raton, Florida. I started learning to solder when I was 4 years old, and I've had 70 years of dabbling in electronics and about 40 years working for Hewlett-Packard until I retired in 2006. And I put together a little presentation here of about 100 slides to be presented over two separate 1-hour sessions, about 50 slides per session. And as I go through this, if you have any questions, please feel free to speak up. I'm going to give a rather high-level presentation of basic electronics and then go into logic circuits and briefly into computers, so that when I get finished, you'll hopefully have a much better understanding of what's going on with the robot and be able to work more productively with it. And also we'll be taking the mystery out of some of the electronics that you take for granted today, but once you understand how they work, that can give you ideas as to how to create other things to help people in the future. Let me share the presentation. Okay, can everybody see the presentation?
Yep.
So the objective, as I said, is to get a basic understanding of electronics, current flow, some of the terminology, and I'll be giving you some historical information based on links on the internet, some Wikipedia, and you don't have to remember everything I present, but I'll try to identify the things that are of importance, and some of it will be obviously important, some you can skip over. But by naming a lot of the people that did a lot of the discoveries and inventions in electronics, those names will give you links where you can go and do further study if you have interest in doing that. After we've finished with this course, you'll have a much better idea of what's going on in the clock kit that you'll be putting together in your soldering class. We'll be focusing rather specifically on how a meter works and how to use either a volt-ohm millimeter or a digital voltmeter and properly measure things like voltage, current, and resistance, and do it both in a safe manner, safe as a personnel situation, as well as safe with regard to not damaging the equipment or the meter itself. And I said we're going to do it at a high level. We're not going to have much math, just some multiplication and division and possibly a little bit of squares and square roots. If anybody would like further detail on any of the subjects that we study, please get in touch with me afterward, either on email or DM, and let me know what you're interested in, and I'll be happy to prepare future presentations to meet your needs. Okay, to start with, an electronic circuit or electrical circuit has to have a complete path around in a circle from the source through the device you're operating and back to the source. And the way that works is the electrons flow from the negative terminal on the battery, is where the electrons have a surplus based on the chemical operation of the battery, and they flow through the device that you want to operate, which is called a load, and then through other devices in the path, and we'll talk about the current limiting resistor later on, and they flow back to the positive terminal of the battery where there is a shortage of electrons. And if you understand magnetic theory, if you look at a magnet that has a north and south pole, you probably all know that opposites attract. The north is attracted to the south, but if you put two poles that are identical together, they will repel. So north to north would repel, or south to south would repel. And electrons do the same thing. They're attracted to the opposite. In other words, where there's a shortage of electrons, the electrons are attracted, and the battery actually creates this potential difference between the two poles to make the electrons flow through the circuit. So electron flow is the normal way we talk about it today, but in the old days, before electron theory was understood, they thought that the current flow or the electricity was from the positive to the negative terminal, and that's referred to as classical current flow or classical current direction. And a lot of the symbols that you'll see in electronic devices, the symbols point to the classic direction of the flow, which is from positive to negative. So don't get confused by that. The electrons always flow from the negative side to the positive, where there's a shortage of electrons. You know, what is a conductor and what is an insulator? A conductor is something that can pass an electrical circuit, where an insulator blocks electrical circuit current. And the conductors are actually made up of mostly metals. And if you think about an electron moving through the wire, it is not a single electron that moves from one end of the wire to the other. It's actually the fact that you have loose electrons in the outer ring or outer shell of the element that makes up the conductor. So if you can see right up here at the top, we have a sample of a couple atoms. We have a nucleus that has protons and neutrons, and an equal number of electrons to the number of protons to balance it out. And the first shell would normally have 2 electrons, then you'd have 8 electrons, and so on and so forth, based on what the atomic number is of the atom making up the element or the metal. And so what actually happens is this loose electron can become free and move to another atom, and now you've got a shortage of electrons here. So if there's another element over here, another atom, that could have an electron move over and take the place of this missing one. So the current flow is actually electrons moving from one element atom to another element atom. And in order of good conductivity, we have silver, copper, and gold that each happen to have only a single electron in the outer shell. And as a result, it's free to move about. But if you have a lot of electrons in the outer shell, the attraction from the protons equalizing the force of the orbit of the electrons in the shell are rather strong. And if you only have a single electron in the outer shell, it's further from the proton, so it can more freely move from one atom to another. Now, an insulator has quite a few electrons in the outer shell, so therefore it would have tightly bound electrons that would not move easily. Insulators are not perfect, though. Even glass, rubber, plastics, air, and water can become conductors if you have enough electrical pressure. An example would be a lightning storm, where the clouds have a large charge and the lightning strike can move between the two clouds through either water or air, and they're actually moving the electrons when the strike occurs. But for all practical purposes, when we're working on the robots with low voltages, the metals are good conductors, and all these other things that are poor conductors will function well as insulators. Here I said the best conductors are silver, copper, and gold, and you can see there's a single valence cell in silver, which has an atomic number of 47. I mean, there are 47 electrons and 47 protons. Copper is almost as good as silver. It also has a single electron, and then gold also with a single valence electron. This is a list of the different metals and other items that can function as either a conductor or an insulator based on its ability to have electrons in the outer shell move. And one thing to consider here is the fact that the resistance increases with temperature, and the conductance, or the ability to conduct electrons, increases with a decrease in temperature. So an example there would be if you have a light bulb, when you turn it on, the current going through the metal in the light bulb heats it up, and it actually decreases the current by increasing the resistance. And the reason the resistance is increased is because all of the different atoms are vibrating and moving as it gets hotter, and that makes the resistance increase and the current decreases. This is a method of calculating the resistance of a conductor. If you know the length of the wire and the diameter, you can actually calculate the conductivity if you know the length and diameter and the material or the conductivity from the previous chart. This calculator is available online, along with several others that we'll be looking at today. I think this is probably one of the most important slides to understand in order to get an understanding of the difference between voltage and amperage and resistance. Voltage is considered and electrical pressure or potential difference that is actually the force that moves the electrons, and that's why it's called an electromotive force. So if you look at this tank of water, the pressure is the height of the water and the weight of the water pushing down. The higher the water is, the more pressure, therefore the more flow you'll have through the pipe. Now, if you have a large pipe, a lot of water can flow through it in a short period of time, so that is considered less resistance. Whereas a small pipe has a more resistance to the flow of water due to friction, so that the water will flow down from the tank more slowly with a high resistance than it will with a low resistance. A good example would be if you have a 55-gallon drum, similar in size to the trash can you take out front every week. Fill that with water and connect a 10-inch pipe to the bottom of it. That tank of water will be empty within seconds. If you use a 1-inch pipe out of that tank, it might take 45 minutes to an hour to drain. And if you take a soda straw, it could take a couple days. Let's say you take 2 soda straws and let the water drain through 2 soda straws. That will drain twice as fast as 1. So you have half the resistance if you have 2 parallel straws. And we'll be looking at that type of analogy when we look at resistors and how we connect them in series and parallel. The alternative to parallel is if you take 2 soda straws and put them one after the other, the water will drain half as fast because it has the friction of the length of 2 soda straws to go through in order to get out of the tank. Here's an example relating the electrical terminals to the water terminals. If we have 1 volt, this is the pressure from here to here that's pushing the water. We have a resistance of 1 ohm, which is a rather large pipe. And if you have 1 volt through 1 ohm, that's 1 amp of current. And you'll see how that's calculated when we discuss Ohm's law shortly. If you have half the size of the pipe, that's twice the resistance, or 2 ohms instead of 1. Therefore, we have half the current flow, or 1/2 ampere. So it'll take twice as long to drain the tank. Okay, so the symbols that are used are A as an abbreviation for amperes, V for volts, and the omega symbol, the Greek letter omega, for ohms. The names of them are ampere or amp, an abbreviation, volt and ohm. And when we write them in an equation for Ohm's law, current uses the letter I, voltage is E or V, and resistance is R. And you can read these at a later time if you like. I'm not going to go into all the detail, but this is some supporting information as to where these names came from and why we use these names. As an example, George Ohm found that there's a direct proportionality between the potential difference or voltage and the resulting electric current. And that's the basis for Ohm's law. You might want to make a copy of these slides. You could even copy them to your phone as a PDF file and use them as a reference. I don't expect you to remember everything we talk about, maybe 8 or 10%, but I'll identify the things that are most important. Amperes and coulombs are related in that coulombs are the amount of electricity transported in 1 second by 1 ampere of current. And you don't need to remember this so much as to get some idea as to how small an electron is. If we look at the charge needed to make 1 coulomb or 1 ampere per second in a wire, the number of protons is 1.6 times 10 to the minus 19. Actually, that's the charge, minus 19. The number of the protons in a coulomb is 6.241 times 10 to the 19th. Well, if you had 10 to the 6th, that would be a million. 10 to the 9th would be a billion. 10 to the 12th would be a trillion. And it's hard to even imagine that many electrons being moved with 1 ampere of current. So it's an infinitesimally large number of electrons in an ampere. We use batteries and cells to power our devices. A cell is simply 1 unit of a battery made up of multiple cells. And we talk about A AA battery or AAA battery, they're really not batteries because they only have one cell which produces 1.5 volts. If we put them together into a battery and put them in series so their potential adds, we have a pressure of 9 volts if we have 6 of these cells, each at 1.5 volts. And each cell in a dry cell, like a AAA or a AA or even a D flashlight battery, has a container which is zinc and an acid electrolyte with a carbon rod down the middle. So the positive terminal with the shortage of electrons is at the carbon rod, and the zinc container is the negative with a surplus of electrons, and the chemical process causes that to happen. If you want to use a battery over and over again, you would use a storage cell instead of a primary cell. And they may be recharged and reused. The car batteries use lead plates with a sulfuric acid electrolyte, and each cell is approximately 2 volts. 6 cells in series gives you 12 volts. Now, you never would want to discharge the battery down under 12 volts or it would be damaged. The life of a battery is retained if the battery is kept well charged and never discharged beyond a safe point. The battery in a car would typically have about 12.6 to 12.7 volts fully charged and right at about 12 volts when it's discharged. And while you're charging it, the voltage rises to between 13 and 14 volts until you charge it, then you remove the charger. The same is true of the batteries in the robot. And in order to get the best life out of those batteries, after use, they should be charged right away and stored in a charged fashion, and that way they'll last quite a long time. If they're left discharged for quite some time, they will not hold a charge. Different types of batteries, such as nickel cadmium or lithium ion, have different voltages of the cells and have different charging requirements, and it's important to study specification sheets on the batteries to make sure they're properly maintained when you use them. Your cell phone has electronics in it that keeps track of the charge and warns you when you need to charge it, so the battery life is maintained. So Ohm's law is a simple equation of current, which is I, is equal to the voltage E divided by the resistance R. And algebraically, you can rearrange that to be resistance equals voltage over current, or voltage equals current over resistance. That's the E equals I times voltage equals current times resistance, which is E equals I times R. All you need to know is 2 of the factors and you can calculate the other one. And if you look at this symbol here, you can read it as I is equal to E over R. That's current equals voltage over resistance. E equals I times R, and R equals E over I. So that symbol can remind you of what the formula is until you've memorized it. The switch is a device that allows you to break the flow of current. And since the flow of current goes through a metal wire, if you put something in between that allows the wires to be insulated from each other, then you stop the flow of current because you don't have a complete path. And you can mend the circuit by actually allowing the 2 pieces of metal to touch. So you have metal in the switch, which connects to the wires, and another piece of metal that connects those 2 terminals together and allows the current to flow. This is a push button switch. This sample here is called a mercury switch, and it has 2 wires and a glass enclosure with some liquid mercury. And those are used in the older thermometers and thermostats that control your house temperature, with a bimetallic bar actually tilting the switch and moving the mercury to either contact or release from the wires. This is a rotary switch that can be connected from one point to many different choices to make a selection. This one's called a dip switch, which is a dual inline package switch that is identical in size and shape to most of these 16-pin integrated circuit semiconductors, and it has 8 individual toggle switches on it. This is a button switch like you'll be using in the clock kit. This is called a reed switch, which is 2 pieces of metal in a glass enclosure, and that's operated by a magnet. You could put a magnet in your door and mount this in the door frame that's stationary and be able to determine whether the door is open or closed based on whether the magnet closes or opens the switch. You all know this one is just a regular switch for turning on lights and other appliances in the home. This is called a toggle switch. This is a light switch that can be put on a lamp cord to turn it off away from the lamp. Another larger button, a rocker switch, and this one is a micro switch that has a very small, easy to push button with a springy piece of metal attached so that you can put it in a place where something in a robot could push on it as it moves and turn the switch on and off to determine position of a device. The resistors we've talked about briefly when we looked at Ohm's law, and those are used to oppose the flow of electric current. When you don't want a good conductor, you can use these to drop voltages or to decrease the flow of current. And if you work in electronics for a while, you'll be able to recognize that the color codes tell you what resistance value or how many ohms the resistance is. And on the left, we have brown, black, red, which are 1,000 ohms. The brown is a number 1, the black is a 0, and the red is a number 2, which adds 2 zeros to the number. Here we have one that's 56,000 ohms, green is 5, blue is 6, and the third band tells you add 3 zeros to make 56000, and the gold indicates that the resistor is manufactured to comply within 5% of the rated value based on the color code. The resistors can be made up of either carbon or, more often today, a metal film, and the metal film is actually plated onto a piece of ceramic, and the resistance is controlled based on how much plating is done, and the cross-sectional area of that plating that's inside the resistor body actually controls how much resistance. The bigger the plating is, the lower resistance, because you have more atoms to pass the electrons. The thinner it is, the higher the resistance, and the harder it is for current to flow. Now, if you don't want to have to use the chart of color codes to determine the resistor value, there are tools online. But if you'd like to do it just with a chart, we have resistors on this chart here that show the black is a 0, the brown is 1, all the way on through 9, and the gold and silver are your tolerance values. And on this resistor, we have actually 4 bands. So this has 3 significant digit bands plus a multiplier, where this previous resistor had only 2 significant digits and a multiplier. This all seems like a lot to learn, and it's really easy to deal with if you go down to your website, use your Google search on resistor calculator, and all you have to do is use the radio buttons, choose what the colors are for each of the bands, and it will calculate it for you, which is much easier to do if you haven't learned or memorized the charts. The symbol for a resistor is a jagged line showing that it takes a good bit of effort for the electron to get from one end of the wire to the other. And resistors in series, just like the soda straws one after another, have more and more resistance as you go from one end to the other. And so the resistors add, so if you had, say, 10 ohms in each resistor, and you have 4 of them, add them up, you've got 40 ohms total. Now, if you had resistors in parallel, that's like putting 4 soda straws individually on the water tank and draining it with 4 in parallel, and it drains 4 times as fast. The same thing is true here. You have 1/4 of the resistance. So if you have 4 resistors that are 40 ohms each and divide that by 4, you'll end up with just 10 ohms, 1/4 of the 40. This is the formula that's used for calculating resistors in series. You simply add up the sum of all the resistor values and you have the total. The formula is a little bit more complicated for resistors in parallel, and there are calculator programs on the web to solve that too. Here's that problem solved with 230 ohm and 120 ohm resistors. If it was 330 ohm resistors, you can see a third of 30 is 10. So 8.57 is what you would end up with if you had the 20 ohm resistor instead of a 30. And there's the same calculator program, a different section of the page used to do that same challenge. We just simply list the three resistor values, press the calculate button, and you can see the 8571 resistance is the same as what we come up with here. So here's a bit more complicated circuit that has several resistors in it, both in series and in parallel. And the way you would do this calculation is you would break it down and take these two resistors in series, add them to get 10 plus 1, which is 11, then use the formula to calculate 11 and 4 and 12 in parallel, and then add that end result to this 1 ohm, since this group of resistors represents one big resistor that you calculated the value of in series with this one. And so now you can calculate any one of the resistors if you know the other ones. Interesting term here is the mho. Up until now, all the different electronic terms have been named after people that discovered or invented. Mho is simply ohm spelled backwards, and that's the inverse of resistance, which is conductance, or the ability to conduct electrons. So Anthony mentioned Kirchoff's law in one of our team meetings a while ago, so I decided to add that into the presentation. And that has several laws that help us analyze circuits that are more complex than this one. And this one you can see right away that you have two resistors in series, and that's in parallel with these. But if you have a matrix of a lot of resistors or other components, there are a couple laws that help you calculate that we can thank Kirchoff for. And here are the laws. One of them is that if you have a circuit with multiple devices and a source, the voltage drop across all the devices added together is equal to the voltage in the source. Or another way to say it is the sum total of all of the devices in the circuit is 0 when you take the signs and add algebraically. So this would be a positive source, and these would be the negative, which is a load. So this number negative added to this number positive would always be 0. And in order to analyze a complex circuit, one of the tools he gave us is the fact that at any node or point in the circuit where there's a junction where multiple devices connect, the amount of electrical current or number of electrons flowing into that point is equal to the number that are going out. So if you're trying to analyze a circuit and determine the flow, you can compute some of those to see which way the current is going. And once you figure 2 or 3 of them and figure the values, then you can figure what the other one is. So Kirchhoff's laws help us analyze the more complex circuit, but that's probably beyond the scope of what you'd be doing with robot. Okay, we talked about volts and amps and resistance. If you take the volts and multiply it times the number of amps in a circuit, you end up with watts, which is the amount of power you have. And you can do the same calculations based on having a knowledge of only the current and the resistance, and still calculate watts by multiplying resistance times the current squared, or you can calculate watts by squaring the voltage and dividing by the resistance. So either you know the voltage and the current, you know the current and the resistance, or the voltage and the resistance. In any case, you can calculate the watts. And there are some examples here of the results of the calculation. For example, 50 volts at 10 amperes, multiply them together. You have 5 ohms if you calculate the resistance, and 500 watts with 50 volts. Energy takes into consideration the watt, which is the rate of current flow, and the amount of time it's flowing. So a joule is a watt of energy for 1 second. And this is valuable when you're looking at what is actually accomplished by the electrical circuit. If you just have a current flow of 10 amps and a certain voltage, but you don't take into consideration how long that is happening, you have no idea how much work is being done. But the work accomplished has to do with the actual rate of electrical flow in relation to the amount of time it occurs. And that leads right to your electrical watt meter at the house. If you have a 100-watt light bulb and you leave it on for 24 hours, that consumes 2,400 watt hours of energy consumption, and that's equal to the 2.4 kilowatt hours. 2,400 is equal to 2.4 kilowatts. And at 10 to 15 cents a kilowatt hour, you could sit down and calculate how much it would cost if you left that light on in the garage, consuming 100 watts for 24 hours. One day wouldn't be that bad. If you leave it on for a month, you'd be spending quite a bit of money, and it's much better to use that for something useful. If you take a toaster that uses about 3 amperes to heat your nichrome wire element to heat the toast, the nichrome wire heats up to red hot, and the infrared rays will actually toast and brown the bread. You can see we have the voltage of 120, the current of 3 amperes, and 40 ohms of resistance. And if we want to figure out the power used, we can figure it 3 different ways, just like I showed you in the previous slide. The same formula with volts and amperes, or volts and resistance, or amperes and resistance. The result is always the same. So this is just a slide that gives you some comparisons as to what power is used by different things. An air conditioner between 20 and 25 amps at 240 volts is going to be around 1,000 watts, or no, 1,400 watts. I'm sorry, let me do that again. It's more like 4,800 watts for a 20 amp at 240 volts. Your stove with all the burners lit and the oven on is about 50 amperes. So you're talking closer to 12,000 watts with a stove. As a comparison, light bulbs would only take 100 watts in the old days, but LEDs only take 14 watts to make between a 60 and 100 watt bulb light output. And when we look at the robot, we're looking at only 12 volts of power instead of 120. So to do the same amount of work in the robot with 12 volts available, the current would be 10 times what it would be with your 120 volt house power. And if you looked at the post that Radu posted today on Discord, he said one of the challenges might be to compare what the use is of a wall receptacle power at home compared to the battery on the robot. And this is what we're doing here. When we look at the motors and the actuators on the robot, since they consume many amperes, the resistance and all the wiring must be minimized. And there was a time last January when one of the robots was failing, and the failure looked like it was a computer problem in the Robo Rio, because the computer would just stop computing and wouldn't communicate with the driver station. And it turned out the battery had a problem and the voltage was dropping when the motors were running with a lot of power, when they were doing heavy acceleration, and the voltage would drop enough that the actual computer in the Robo Rio would fail due to the lower voltage. We thought it might have been a problem with the wiring, but we narrowed that down with battery tests to the fact that the battery was causing the problem. But to make a reliable robot, it's very important that all of the wiring, especially the heavy high current wiring from the battery to the breaker assembly, be secure and tight and good clean connections.
Just an update to that. In fact, after you left, we found the real problem. It turns out that the wire from the battery to the power distribution frame or power distribution unit through the circuit breaker was not tied down very tight. And in fact, when we took it apart, it had all melted. Wow. And it turns out that that connection was loose, and that was the cause of the problem. Once we fixed that, we never had that problem again.
So like Keith said, it's very important to make sure we have tight connections to make the robot reliable. So your wire size has to do with how much current needs to flow through the wire without a voltage drop. And if you have too small a wire for the amount of current you're having flowing through it, the wire gets warm due to the friction between all of the atoms and the voltage drops, and that actual energy is consumed by heating the wire. So larger wires for larger current, smaller wires for smaller things. And the sensor circuits consume extremely small amounts of power, thousands of an ampere, which are milliamperes, or even in other cases, microamperes or millions of an amp. So the wire size needs to be large enough so that we do not damage it while we're working on it. But a hair fine wire is big enough to carry these signals between devices, and the sensors operate at anywhere between 5 and 12 volts.
And just an aside too, the way we found the problem was we put a voltmeter across the battery, found out that it was, let's say, always 12 volts, but then we put the voltmeter across one of the motor controllers and ran the motor, and we noticed that the voltage dropped, let's say, to 7 or 6 or 5 volts. So basically between the, so we knew that there was a resistance problem between the battery and the motor, because the motor was running at 5 volts and the battery was at 12 volts. So something was wrong between those 2 points. And we eventually figured it out and found out that, in fact, the wire was not tied down very good on the power panel. And in fact, it overheated because of the resistance and caused a very nasty wrecking of the plastic. So it's very important to understand what Mr. Rick just talked to you about.
And that's a very timely statement, Keith, because what we're going to be looking at now is how to use the meter to measure voltage, current, and resistance, and how to actually isolate that type of problem by looking at a schematic and where we will put the meter to make those measurements. So the important thing to notice here is that to measure voltage, you use the meter probes across the component of interest, which means if you want to measure the battery voltage, you put the black lead on the negative terminal of the battery and the red lead on the positive terminal of the battery. And that's measuring between the 2 terminals of the battery. But if you're measuring current, you're actually having to get into the circuit and break the wiring and put the meter in between the wires to actually sense the current that's flowing within the resistance, within the wire. And resistance is something that the meter can measure by using its own battery, its own source of energy, and its own sensing circuit. And so it puts the current through the device you're measuring and calculates the resistance of that device. So you cannot measure resistance if the device is in a live circuit with current flowing through it. Here's a picture of a meter similar to what we'll all be using in the class for soldering, and a chart on the right showing the typical symbols you'll see on the meter that identify the different functions. And if you look on the knob of the meter, which is the round piece with the diagonal bar through it, you'll see a little dot on the left where it's painted black. And I would suggest that those of you that get meters actually take the meter, look at that bar and find the little dot and take a black or some other contrasting color permanent marker and mark the end of it, because it's very easy to misposition that switch in the wrong direction and actually damage the meter or damage what you're working with if it's in the wrong position. So that little dot is very hard to see without actually putting some color on it. Right now, the meter is set to the 20 volt range. DC volts means you're going to measure direct current. And over on the top would be the position which is used for AC volts. Since time is of the essence right now, I'm not going to go into all the details of the meter, but that can be taught in the actual hands-on soldering class when you're actually going to measure devices. And in that class, you'll be testing the components that are going to be used to build the clock kit. You'll test the resistors, you'll test the capacitors, the transistors, and so on, and get a feel for using the meter for measuring individual devices, as well as measuring voltages and current. So some of the precautions you should take when using the meter is if you're measuring high voltages or unknown voltages, start with the power turned off, attach the meter leads with alligator clips, and then apply the power after setting the meter range switch to the highest scale value, and then move the scale switch down as you determine what the voltage is to get a little bit more resolution. For example, if the meter is set to the 1,000-volt scale, all 4 digits are used to display the whole number of the voltage. But if you move it down to the 200-volt scale, now you have 3 digits of units plus 1 of tenths. And as you move down to lower scales, you'll actually have more resolution for measuring low voltages. You never want to attempt to measure resistance on an energized circuit because you could damage the meter or the device you're measuring and you won't get a valid reading. And of course, never measure across a voltage source with the meter in the current position. And once we discuss how meters work internally, you'll have a better understanding of why that is. Okay, here's an example of measuring the voltage. And as Keith said, measuring the voltage across the input to the motor controller is an example we're looking at here, where the motor controller is the load. And you can also measure with the meter from the plus and minus to the battery, which is the V on the left, and they should be basically equal. If they are not equal, you could actually measure from the top of the battery where the plus is to the left side of the load and run the device with current through it. And you should not see more than a very, very small fraction of a volt, thousandths of a volt or even millionths of a volt, since the wire should be a good conductor. And if that reads okay, you can also try reading the negative side from the bottom of the battery over to the right-hand side of the load to see if the wire has any losses. And once you identify that there's a voltage drop in the circuit, then turn off the circuit, remove the battery, inspect all your connections, look for bad splices and loose terminals. And once you make the correction, redo the measurements to determine that the problem is resolved. Here's a meter connected to measure current, and we've actually broken the current path between the battery and the load in order to actually measure the current going through the wire. And in this mode, the meter has a very low resistance, so it won't add to the resistance of the circuit significantly. And this is why we can't connect the meter in current mode across a battery, because the resistance is so low, you'll actually have fireworks. You'll damage the meter, it'll blow the fuse in it, and it'll be useless if the fuse damages other things in the meter as it blows. When we do the soldering online course, I'll have an actual meter broken down where you can see what's going on inside of the meter. A Clamp-On Ammeter is used in robotics to measure current without actually breaking the circuit. And later on in this course, I'll describe how the Clamp-On Ammeter works to measure current through a wire without actually breaking it. I think we've covered resistance measurements pretty clearly, but if you print the document, you'll have this as a reminder of the precautions and the procedures to measure resistance. To measure power, as you remember, power is the voltage times the current. And so you can either take 2 meters, using one to measure the current and the other measure the voltage, and then multiply the readings together to get the number of watts consumed. Or you can measure each individually, one after the other, assuming the current that you're measuring is not going to change over time. As long as it's a rather stable load, you can measure one, then the other, then do your calculation using only 1 meter.
Yeah, just go back to that picture there, Rick. So it turns out that the nice thing about the robot stuff is that the motor controllers have logic inside them to measure the voltage and the amps. And so in the software, we can print out the volts and the amps. We can also print out the volts times the amps to figure out what the power is. And each motor has a different rating of how much watts it can handle. And so, for example, when we calculate, we can calculate with the motor, we can calculate how much it's able to lift. For example, when we put the lifter on the robot last year, we calculated how big a motor we needed to lift that. And it turns out that the Falcon 500 is capable of supporting about 500 to 600 watts. So you can go through the mathematics and figure out on 12 volts, 600 watts will run about, what, 50 amps. So that's what we typically do in the robot. And the nice thing about the software is you can print that out and you can see how much power each motor is utilizing. So
here's an example of a series group of resistors all hooked to a battery. And with Ohm's law, if you were to take each resistor value and add them up and determine what the total resistance is, now you can determine the current and figure out what the actual power is through the three resistors. There are cases when you might not be able to get access to measure a resistor, or you might have a light bulb in a circuit which you cannot measure the resistance of, because a light bulb resistance increases as the filament element in the bulb heats up to brightness, and it has a much lower resistance when it's cold. So by taking a circuit of this type and measuring the voltage across a resistor, and then if you have only one resistor that you don't know the value of, you can actually calculate what that resistance is based on the other known values using the Ohm's law and the Kirchoff's law. Okay, a diode is a device that's a semiconductor that allows current to only flow in one direction. So if you have a positive voltage on the anode and a negative voltage on the cathode, the electrons will flow. But if you reverse the polarity of the signal and you only have a positive on the cathode and a negative on the anode, no current will flow. So it's a gate that allows current to flow only in one direction. And these can be used for many purposes. One is to convert from alternating current to direct current, and many others. To measure a semiconductor diode, it requires at least a voltage of 0.5 volt to 0.7 volt across the diode in order for it to conduct. So the digital voltmeter has a diode test mode that has the symbol of a diode, and that'll produce enough voltage between the two test leads to cause a current to flow if the diode is connected in the right direction, and you would just reverse the leads to determine whether you do not have current flow in the other direction. On the other hand, the resistance measurements are made with a very low voltage from the meter so that it does not damage semiconductor devices that are sensitive to lower voltages. The capacitors are a device where you have two metal plates in proximity with what's called a dielectric in between them. That's an insulator between the two metal plates, and the capacitor can actually store a charge when you connect it to a battery. So the actual potential of the battery, the voltage, actually then is moved to the capacitor and stored by the capacitor. And then if you were to disconnect the capacitor from the battery, the actual voltage would still be there on the capacitor until it leaks off through the dielectric, which is never a perfect insulator. And therefore you would have a very minute current through the dielectric, but for all practical purposes, the voltage will retain over time. So the capacitors actually are known to oppose a change in voltage, because when you try to charge them, it takes an amount of current from the battery to put the energy into the capacitor. And then of course, when you connect something to the capacitor later on to take the power out, a current flows, and the capacitor attempts to maintain its voltage until the charge is removed. And when the charge is removed, then the voltage goes away. But for all practical purposes, it likes to keep the charge the same because of the number of stored electrons on one side and the shortage of electrons on the other side. Your symbol for the capacitor is just two metal bars with the wires connected to them. And the value of a capacitor is measured in microfarads or farads. A farad is an extremely large value, so most often we use microfarads. And in other small circuits that operate at high frequency, we actually use picofarads, which are millions of microfarads, or what we used to refer to as microfarads. So Michael Faraday is the person that discovered the function of a capacitor. And there's some historical detail here that talks about the static charge being 1 ampere per second is a coulomb. That's storing a positive and negative charge. And if you look at a cloud and another cloud that have different charges, they make up an extremely large, powerful capacitor. And the discharge, when you have a current from one cloud to another, is lightning going through the air and the water of the rain between the clouds. And it's extremely large voltage, up in the multi-millions of volts, actually more than billions, and many, many amperes of current, making the lightning strike bright and loud. There are many applications to capacitors, and we'll see some of them later on in the course and also in the clock kit. The armature is the part of the motor that spins. This coil of wire generates the reversing magnetism, and the way it's reversed is we connect the two wires to these two brass commutator conductors, and then we use copper brushes rubbing against them. So as this turns around, each time it makes half a revolution, it reverses the contacts to this coil, reversing the north and south poles, causing the motor to spin. And as a result, we have something that can generate a spinning force that can do work. Just two poles doesn't make it very efficient, and it can stall in between positions. So to make a practical motor, we break it up into many different poles and have many different terminals on the commutator, 180 degrees opposite, and the brushes contact incrementally one pole after another, and that's how we get a strong rotating force from a motor. The transformer uses that mutual inductance feature of a magnet by virtue of the fact that if you have a magnetic field varying, you'll generate a current through a wire in that magnetic field. And at the same time, if you actually have a current flowing through a wire and turning on and off, you'll actually generate a moving field in the other wire. So this is what a transformer looks like on the left, with the wires coming out. This is the iron core, and the windings are wrapped around the core through the internals of the core here. This is the schematic symbol showing the winding of the primary and the secondary wire and the core. And if you take an iron core of this shape or another shape like this one and wind a group of wires around it and place a current through it, you'll actually induce a current here. The induced current here would be a voltage of twice the voltage that's here, because the voltage ratio is a direct relationship of the amount of magnetic force. And if you only have 5 turns of wire with 120 volts, that would produce 240 volts with twice as many turns, or 10. These 110 and 220 are the voltages we used to have long ago. Now we're having between 120 and 125 on our house power. 5 or 10 turns wouldn't really be sufficient. This is just an example for illustration. You'd have to have a few hundred, maybe 200 here and 400 here. And transformers are used to change the voltage between a high voltage and low, or low and high. They're used for distributing power along the high voltage lines that distribute from the generating plant to the different towns, and then the voltages are dropped to a useful voltage as they're brought into your house. So you might have 7,000 or 13,000 volts on the pole at the house, and the transformer would reduce that to 240 volts, center tapped, which is 120 volts each side for appliances in the house. And if you drop the voltage from double to half, you'll actually produce twice as much current in the output. So you can use much smaller wires to distribute the power from the power plant at a much lower current. And then once it gets to your house, you can raise the current and actually raise the voltage, lower the voltage to a usable voltage and get much more current with smaller size wires, bring it to your house. Now, the Clamp-On Ammeter uses that same method of measurement, but the actual secondary winding in the transformer of the measuring device is this clamp-on jaw here, which is opened by pushing this button. And this jaw then continues the path of current to make the ability to have a single or one turn winding of the secondary of the air core transformer, and the primary is just the wire from your battery to your circuit breaker, and you can actually measure the current from your battery with this device without having to break the wire and put the meter wires in series. And as I mentioned a few minutes ago, there are capacitors that we do not like in the robot that we didn't put there intentionally. But if you remember, the capacitor opposes a change in voltage, and the inductor opposes a change in current. And a capacitor consists of just two metal plates in proximity with some insulation between them. Two wires, in effect, make a capacitor, and the length of the wires from one point to another make an inductor. So these capacitors and inductors cannot be removed from the wiring in the robot, and they play an effect in the wiring between the Robo-Rio and the other devices, such as the motor controllers, or on the I2C buses that are connected to other devices, such as a Raspberry Pi. So the problem we run into here is it takes time to charge that capacitor when we try to put a positive voltage on a wire. And then when we take that positive voltage off or put a negative on it, we have to discharge that voltage. And so this resistance and capacitance in the wires actually causes a delay and limits the amount of speed with which we can put the commands between the Robo-Rio and the other devices in the robot. And so in order to avoid a problem, there are some constraints that restrict the number of inches of wire we can have between the different devices and the different buses, and also require that we terminate the bus at the end, such as on the CAN bus where we have a resistor. So the fact that we cannot get rid of capacitance and inductance and resistance where we don't want it makes a challenge for AC circuits, and DC circuits don't have a problem with it because we have a static current or a static voltage. But with alternating circuits, it's a big part of electrical engineering to deal with these stray capacitance and inductance that we have no control over. Okay, I told you we'd talk about briefly how a resistor controls the current through an LED. And you remember the resistor opposes voltage, opposes a current, or makes it hard for current to flow. And the purpose of the resistor here is the LED is a very sensitive device. It takes a very small amount of current and it's a very small voltage. And if you connect the LED directly to the battery of 9 volts, since the LED has such a small resistance, the current from the battery will damage the LED instantly. You'll see a flash of light, and after that, the LED is dead, won't work anymore. So what we do is we put a resistor in series with the LED to limit the current flow in the circuit. And if we use a resistor somewhere between 200 and 2000 ohms, we'll get a nice bright LED, but it'll be protected from damage. Now, Galvani discovered the principle of electrical current that made a dead frog's-like jerk, and he invented something called a galvanoscope, which is a device that would be able to measure extremely small currents, much smaller than we could measure before. And a gentleman by the name of D'Arsonval, along with Marcel Duprez, actually developed it into a useful tool called the galvanometer. And that's basically what looks like a motor that's limited in rotation by a spring. There's a picture of an early device, and it has a scale with a pointer. And as the armature of the motor moves back and forth, the scale can indicate the amount of current that's being used to produce that movement. If we look at a diagram of how that actually functions, you see what looks like a motor there with the fixed field poles, north and south permanent magnets, and the armature with the coil around it. But instead of attaching bearings to it, we've attached a needle with a pointer, and we have what is called a pair of hairsprings in blue. And the hairsprings are used for two purposes. Number one, they're used to connect the negative and positive wires to the armature of the meter movement. and they're also used to provide a resistance to rotation such that at rest, the pointer is all the way over to the left, which would be the 0 position on the meter. And if the scale was 0 to 10, when you energize by putting a current through that coil, it'll pull it in a clockwise direction. So the pointer will now turn over to the right to the 10 position. And these meters are extremely sensitive. They can measure down as far as a milliamp on the older ones, and the newer ones can measure a full scale reading with as low as 10 to 50 microamperes, or 10 to 50 millionths of an amp. I'll go briefly over the shunts and the series resistors. As we said before, if we add a resistor in series with a circuit, we reduce the current through the circuit. So if we want to make a useful meter for voltages more than 1 or 2 volts, we could take a 1,000 ohm resistor, and that would allow us to have 1 milliamp or 1,000th of an amp of current. If we have a 1 volt source, that would provide the 1 milliamp that the meter needs to get to the position of 10. Let's say we wanted to measure 100 volts. All we would need to do is make that resistor 100 times the 1,000 ohms. So if we make it 100,000 ohms, we reduce the current to 1 milliampere, even if we have 100 volts. And now the meter will read from 0 to 100 volts with that resistor in series. And as you turn the switch on your digital voltmeter, that same resistance functionality is used in the digital voltmeter to be able to have multiple meter scales. And on the smaller, lower scales, we have much smaller resistors that are selected to measure smaller voltages. Now, if we want to measure current, we don't want to put a large current through the meter. So we use a very, very small resistor that will have a very, very small voltage drop when current flows through that. We put it in series with the remainder of the circuit, like I showed you when we measured current with the resistor, with the ammeter and the load. And now we place the meter element across that very, very small resistor, which would have a very small fraction of a volt, even if you had 10 or 100 amps going through that small resistor. And now you're reading a very, very small voltage. And we're also affecting the circuit very little because we're adding a minute amount of resistance to the circuit, and it doesn't affect the amount of current flowing when we measure it. That's actually called a shunt. A multiplier is used to make the meter read a higher voltage. A shunt is used to make it read a higher current. Lost my control here. Okay. So we're down to halfway through where we'd actually be going into electronics instead of electrical. So this is probably a good time to stop and then continue tomorrow at 7 p.m.